The commonest notion of what constitutes dispersion, however, is what is known as the standard deviation. The standard deviation is an average deviation from the middle of the data. It is calculated using another term called the variance. Before I show you what the formula looks like, let me take you through a calculation of the standard deviation and the variance. Consider again our mutual funds. Let's line them up as a column of numbers. The first step is to calculate the mean, the arithmetic mean, average. Add up the 10 numbers, divide by 10, that gives you 12.28, which is the average return. This is the arithmetic mean, or X bar. The second step is to take the deviation of every observation X from the average X bar. In other words, 12 minus 12.28 is minus 28. Minus 0.28. 0.28 observations below the average. Do so for all the observations. Remember, we're talking about dispersion here. Dispersion means variation. Variation could mean being high and low. It's different from the average. And if we are measuring consolidated variability, we ignore the fact whether it's dispersed because it is above the average or dispersed whether it is below the average. So what we do is we square up the number. 0.2 minus 0.28 squared gives me 0.08 to 2 decimal places. So I calculate the squared dispersion from the average, the squared difference from the average. I do that for all my 12 numbers. For example, my smallest number 9 is more than 3 units away from 12.28, which gives a squared dispersion of more than 10. The next thing that I do is I calculate the total dispersion, or what is called the total sums of squares sometimes. The total sums of squares, which in this case is 5.96. The variance is 6.33, which is 56.96 divided by the number of observations that I have, except that I do something a little tricky here. I should divide by 10 and end up with 5.696. But I don't. What I do is I divide by 10 minus 1, which is 9. So 56.96 divided by 9 is 6.33. This is the variance. What is the standard deviation? The standard deviation is the square root of 6.33. Why do I take square roots? Because remember, my original observations are in percentages. When I've squared and added them up and averaged them up, I've observed something which is an average of squares, squared returns. But I'm not interested in squared returns. I'm interested in something that is in the units of percentages, returns themselves. So therefore, after taking the variance, I take the square root, which leads me to 2.52 as the something that is in the units of percentages returns themselves. So therefore, after taking the variance, I take the square root, which leads me to 2.52 as the standard deviation. Let me lay this out as a formula. So the variance is equal to an average of squares from the mean. The standard deviation is the square root of the variance formula and is on the original scale of the data. A question is often asked at this stage as to why we divide by n minus 1 and not by n. The reason for this will become a little clearer further along in the program. But for now, it suffices to say that the n minus 1 comes because the central value, the x bar, is an estimate of the unknown middle of the data. If I could use in some way a known average of the data and take my dispersion not around a data estimate of the average, but around a known average, I would then divide by n. I know this doesn't make a great deal of sense at this point in time, but when we look at notions of sample and population again, this will come into the picture. An alternative way to look at it might be the following: that if we have a population, if n is the size of a population, not a sample, population with, say, mean mu, and I'm going to distinguish this from x bar because this mu is the mean of the population, then the standard deviation is written as 1 over n, I is equal to 1 to, say, capital N xi minus mu whole squared, where this mu is not estimated. So if the mean is estimated, divide by n minus 1. If the mean is not estimated and comes from a population number, divide by n, roughly speaking. But almost all calculators will calculate with an n minus 1. I'm sorry, we'll use the formula n minus 1. And if the calculator does not, then we might need to enter manually what that difference is. But unless you're told otherwise, the definition of a standard deviation is with an n minus 1. And it is around x bar, where x bar is calculated for the same data set for which the standard deviation is being calculated. So that is what the standard deviation is. We shall shortly see an interpretation of the standard deviation. Another measure of variation sometimes is used when the standard deviation needs to be looked at, but not as an absolute value, but as a proportion of the typical value in the data or the average. terms like 10% variation in the data or 25% variation in the data. The coefficient of variation, or CV, is a ratio of the standard deviation to the mean. Equivalently, the standard deviation expressed as a percentage of the mean. The standard deviation as a percentage of the mean is usually the CV on the scale of, say, 0 to 100. When is this a useful idea? Here's an example. There are two salesmen working in the same territory. Who's better? Who would you give more commission to? One of them achieves an average of 50 sales, 50 units per year. Year on year, he sells on the average of 50 with a standard deviation of 5 units. Does he sell 50 every year? No. Does he sell more than 50? Some years. Less than 50? Some years. And the square root of the average squared dispersion around that is 5 units. For the second person, he or she sells 75 units on the average with a standard deviation of 25 units, more variable. Sells more, but is also likely to sell less or likely to sell more. The spread around his sales is a lot more. Who's better? In terms of averages, certainly salesperson 2 sells more than salesperson 1. In terms of variability, salesperson 1 is a lot better than salesperson 2. With salesperson 1, you know what you're going to get, compared to salesperson 2, for whom you have less knowledge of what you're going to get in a given year. The coefficient of variation for the first salesperson, standard deviation by mean, is 5 by 50, 0.1 or 10%. The same number, the coefficient of variation, is 27 by 75 or 33% for salesperson 2. Don't get carried away by averages. Consider variation, and in this particular case, consider risk. In finance, for example, the variation, the standard deviation, is a standard measure of risk. If you want more returns, look for higher means. If you want less risk, look for lower standard deviation. In fact, the coefficient of variation in that particular case, it often has a special name and is related to a concept called the Sharpe ratio in finance, which captures this idea of dispersion relative to the mean. Let me dig a little deeper into what the standard deviation actually means. What does it refer to? How do I understand or interpret the notion of a standard deviation? A lot of data follows a bell-shaped distribution. Remember the histogram I was talking about? So if you look at the histogram of the data and then you draw a curve through it, it follows a shape, a bell-shaped distribution. We shall use the term normal distribution for this in due course. If you have such a bell-shaped distribution and you consider the mean, which we shall refer to as mu, and the standard deviation, which we shall refer to as sigma here, if I look at mu plus minus 1 sigma, a 1 standard deviation variation around the mean, that contains 68% of the data, approximately. So therefore, what is 1 standard deviation? 1 plus minus 1 standard deviation around the average contains 68% of the data. What's standard about that? Well, this idea extends to other ranges as well. For example, you might say that let me think in terms of 95% coverage of the data. 95% of the data is contained within plus minus 2 standard deviations. The more usual notion of coverage, shall we say. 99.7% is covered by 3 standard deviations. So, for example, if I say that my mutual fund on the average gives 12% with a standard deviation of, say, 2.5%, what I'm saying is that 12.28 plus minus 2.52 will contain about 2/3 of my data. 12.28 plus minus twice into 2.52, or about 5, will contain about 95% of my data. That's what standard deviation does. Depending on your notion of standard, you might want to think in terms of 1 standard deviation or 2 standard deviation as covering the data. So, if I go back to salesperson 1 and salesperson 2, what did this example tell me? This example says that in 95% of the years, salesperson 1 will give me a return between 50 plus minus 2 into 5, which is 40 to 60. So 95% of my years, 19 out of 20 years, salesperson 1 will sell 40 to 60 units for me. What is the corresponding number for salesperson 2? 75 plus minus 2 into 25, which is 25 to 125. So 95% of the time, 19 out of 25 years, 19 out of 20 years, salesperson 2 will give me 25 to 125. More dispersion. So if you want to cover the risk, perhaps instead of looking at 50 and 75, you may want to look at 40 and 25. The worst case scenario in some way. This is what standard deviation allows you to do. Look for a typical deviation around the average, either through 1 standard deviation or 2 standard deviations or 3 standard deviations, depending on what constitutes your notion of variability. There is an interesting theoretical rule here called Chebyshev's rule, which says that however many standard deviations away from the data you are, there's a limit to how much data can lie outside. So it says this, for example, that if you have 2 standard deviations away, 1 over 1 plus k squared, which is 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 75%. Chebyshev's rule says that 75% of the values will be within plus minus 2 standard deviation. When is Chebyshev's rule useful? Used when data is not bell-shaped. If the data is not bell-shaped, Chebyshev's rule gives conservative bounds for what the 68%, 95%, and 99.7% are. So it gives ballpark numbers for peculiar distributions. Let's come to the close of this simple descriptive analytics of one-dimensional data by summarizing it through a certain set of numbers, the so-called 5-number summary. What are these 5 numbers? The smallest, the first quartile, the median, the third quartile, and the largest. Now, in certain ways, each individually is a measure of location, particularly the median and the 2 quartiles even. The difference between them are measures of dispersion. Q3 minus Q1 is interquartile range. Largest minus smallest is the range itself. But the 5-number summary is a useful thing to carry around to represent data. Even if you have 1,000,000 observations, instead of dealing with 1,000,000 observations, why not deal with just 5? That tells you a great deal. It tells you where the numbers lie, the smallest to the largest. It tells you the middle value, the median. Arrange them all and take the middle value, the median. It tells you an upper value in the sense of the 75% point. It tells you a lower value in the sense of the 25% point. It also tells you about the shape of the distribution. If the distribution is symmetric, Q2 will roughly lie in the middle of Q1 and Q3. If the distribution is not symmetric, then the quartiles Q1 and Q3 will not lie symmetrically around Q2. Lots of data show up as right skewed, a few large observations, in which case Q1 and Q2 will be closer to each other. Q3, representing these large observations, will tend to swing out. The same for left skewed data. Skewness is an idea that represents the asymmetry of the distribution. The more skewed it is, the more asymmetric it is. The more asymmetric it is, the more far away Q2 is from the middle of Q1 and Q3, which can be measured by numerical ways of saying what is the difference between the median and the smallest, the median and the different quartiles, etc., etc. And you can have sophisticated formulas for these things, which often are back of the envelope ways to see whether I have a problem on the upper tail of the data or on the lower tail of the data. You may choose to use these formulas, or you may choose to go for more graphical representations. Here is a graphical representation of the 5-point summary. It is called a box plot. Strictly speaking, it's called a box and whisker plot. The middle is the box, and the two flanks of it are sometimes called whiskers. What is the box? The box consists of Q1 to Q3. What's the line through the middle of the box? The median. Where does the box end? From the smallest to the largest. So the box plot shows you the central tendency of the data, the dispersion of the data, the skewness of the data. It also may show you potentially outliers if you get a little more clever with how the box plot is designed. And we'll get to that soon enough. Now, the box plot can be shown vertically or horizontally and can be used to represent, often as a number of box plots, what the 3 characteristics are, including asymmetry. As you can see here, different kinds of asymmetry lead to different kinds of box plots. If the data is very skewed, then the box plot will tend to extend itself with a very long whisker on one side. This sometimes doesn't come across as being very representative on the data. So the box plot is sometimes reshaped a little bit to stop at a certain point and say that if you are above this point, I will not extend the whisker, but I'll simply indicate a point above as an outlier. So when does this line stop? This length is 1.5 multiplied by the interquartile range. So the box plot extends to the maximum value of the data. But if the maximum is very large, it only goes up to 1.5 times the interquartile range and stops, and then shows data points outside it separately. So the box plot becomes now a device for showing outliers as well. Not just one, but however many there are. There are other plots that are available. For example, quantile plots, which we'll see soon. Scatter plots for multiple dimensions of data. But in summary, all these graphics are showing different characteristics of the data. Central tendency, location, dispersion, skewness, outliers, maybe shapes of the data. Let's see. Sometimes different graphs, different kinds of pictures show different kinds of things. Here's an interesting situation of two histograms. Remember histograms? Bin, classes, bins, frequencies. These two histograms that you see on the left have the same box plot because they have the same minimum, the same maximum, the same middle value, and the same quartiles. But they have different distributions. The top distribution is what you might call bimodal, and the bottom distribution is what's called unimodal. So in this particular case, the box plot loses the information on the mode, something that the histogram is very good at doing. So the box plot is very good at quantiles, medians, Q1, Q3, but not good at modes. So good descriptive statistics often involves looking at multiple graphics, multiple dimensions. What is a quantile plot? A quantile plot is a display of data that sorts it as if they were all equally spaced. Xi sorted and increasing, where Fi indicates what percentage of this data. So F at 50 means the middle value of the data. At 75 is the 75% point of the data. At 25 is the 25 point of the data. So essentially, this is Q3, Q1, Q3, median. So it generalizes the notion of what a box plot is and talks not just of quantiles, but percentiles, which is instead of looking at 25, 50, and 75, look at possibly all percentages. Or more generally, all quantiles. What happens if there are outliers or there's a shift in the distribution? Then the quantile plots of the two distributions will look a little different. Here are the plots of branch 1 versus branch 2 interpreted as a quantile plot. And the fact that they do not lie on a 45-degree line indicates that the two distributions are not the same. In future sessions, you might see this trick to compare not just two distributions, but also to compare one distribution versus a given shape, for example, the bell-shaped, and ask, is my data consistent with a bell-shaped distribution or not? So the quantile plot is a way of looking at comparatives of different distributions. But there's a simpler way to look at different variables, two variables. One of them is to simply plot the two variables on two different axes. This is what is known as bivariate data. What does the term bivariate mean? It means that instead of observing one characteristic in an observation, I'm observing two characteristics in an observation. In the mutual fund example, we saw only the returns, one number. Here, we shall see price and items sold, two numbers. For example, for an individual, we might see height and weight. For an image, we might see size and the number of different colors. We might see different things, different features as they're called, computed for the same observation. If the number of different features is 2, that is bivariate. Each pair of values can be treated as a coordinate in a plot if there are just 2 of them. Here, for example, we're looking at unit price and items sold. And we see this particular graphic or pattern that emerges. And a business might be interested in knowing, what does that tell me about my prices? What prices should I therefore have to ensure that I sell the maximum amount? What is the relationship between items sold and price? Can I find that as an equation, or even before that, can I see that as a picture? And that picture is a scatter plot. You can see scatter plot in different dimensions, as we might see, or many scatter plots capturing many variables. Before we go there, let's look at the notion of correlation associated with scatter. What is correlation? Correlation is the idea that as one variable increases, the other variable increases with it or decreases. Are the variables moving in the same direction, or are the variables moving in opposite direction? The left-hand plot here is an example of positive correlation. The right-hand plot is an example of negative correlation. The bottom picture is interesting because it shows negative correlation on the right side and positive correlation on the left side. And together, this might end up showing that there is no correlation. Not indicating that there's no relationship, but indicating that multiple relationships are present in the same scatter plot. Data could be uncorrelated, no pattern whatsoever. And a warning, the plots on the right also show uncorrelated data, despite the fact that there are large white spaces. They don't show patterns, and they're an artifact of the way the plot is plotted, of the range of values that is allowed. So very often patterns are visible not because of a pattern inherent in the data, but because of the way we have laid up the graphic. So please be careful that when you lay out the graph, make sure that the axes are the way you think they are, and do not give a false picture of association. Putting all this together, we can visualize data in a variety of ways. We can, of course, look for patterns, trends, irregularities. We can summarize it. We can look at various kinds of orientation techniques for data. And there's a plethora of visualization methods that are used, that higher order graphical software, beyond even what classical statistics was designed to do, will allow you to look at. As we saw in a previous session, the ability to visualize is one reason why statistics is advanced. And in fact, a lot of the subject has advanced beyond statistics to very sophisticated graphics that statisticians had not imagined in the earlier days of the subject when fewer computers were available, or maybe none at all. So there are various visualization techniques that I won't take a lot of time on at this point. Different kinds of colors, different kinds of shadings, different kinds of combined variable representations. This is a scatter plot of different variables, 4 variables, latitude, longitude, depth. 4 variables are computed. And these are scatter plots of those 4 variables against each other. So obviously the diagonals is a variable against itself. So it is the 45-degree line. And of 4 variables, there are 6 combinations possible. These 6 plots. The remaining 6 are copies of the same. So it's a way of looking at scatter plots, 2-dimensional plots put together, giving a multi-dimensional representation. Bivariate graphics for multivariate visualization. 2 to many. Before we end this session, some numerics on what to do with correlation association. First, correlation with nominal data. Remember what nominal data is? Nominal data is data that represents names, not variables themselves. Consider here a data set in which you have a table of 1,500 individuals, and they're looked at in terms of 2 nominal variables. Do you like science fiction or do you not like science fiction? The second variable, do you play chess or do you not play chess? Of the 1,500 observations in this sample, 300 play chess, therefore 1,200 do not. 450 like science fiction, therefore 1,050 do not. And this 450 is composed of 250 who also play chess and 200 who do not play chess. So ignore the parenthesis numbers for now. 250 plus 200 gives 400, 250 plus 50 gives 300, etc., etc. Are these variables associated? Is there a relationship or a co-relationship between liking science fiction and playing chess? Now, if that was the case, then what would have happened? Let me give a brief rundown as to how this calculation could be done. If I look at everyone in the set and I ask the question, what proportion of people played chess? And the answer would be, if I ignore science fiction, that's 300 divided by 1,500. Now, if I look at those who like science fiction, and I believe that whether you like science fiction or not has nothing to do with whether you play chess, then the same proportion, 300 by 1,500 of the 450, should like science fiction. The proportion of people who play chess shouldn't depend on whether you like science fiction or not. So, of those 400, how many should play chess if there is no association? It is 300 of 1,500 expressed as a fraction of 450, which is 90. This is the calculation that is done. Row total, column total, divided by grand total gives the expected counts if there was no relationship between the row variable and the column variable. Using this formula, I would have expected to see about 90 people who both play chess and like science fiction, based on this proportion calculation. But my data says that no, it's not 90, it's 250. Many more people than you would expect like both science fiction and play chess. So let me compare this 250 with 90. 250 minus 90. And I normalize that using a rationale that will become clearer in future sessions. to say, look at the difference between 250 by 90, measured as 250 minus 90 whole square divided by 90, observed minus expected whole square divided by expected. Do this for all the 4 cells and add it up. This is called the chi-square statistic. And if this number is large, then one would say that there is an association or the correlation between these two variables. How large is something that's going to take a little bit of figuring out. But very roughly speaking, this is compared to the number of rows minus 1 into the number of columns minus 1, which in my case is 2 minus 1, 2 minus 1, which is equal to 1. And 507 is very large compared to 1. We will make this a lot precise in future sessions. The notion of correlation is actually a little easier when we look at numbers. Let's look at 2 columns of numbers, A and B. So I'm measuring A in one axis and B in another axis. And my points are AI, BI. Here's what I do. The first thing is I calculate the average of my data set. I calculate a point A bar, B bar, which is the average of all my A's and all my B's. A bar is the average of all the A's. B bar is the average of all the B's. And then I ask the question, when A is larger than A bar, is B larger than B bar as well? If A and B are on the same side of their averages, then this number here is going to be a positive number. When is this product AI minus A bar, BI minus B bar going to be positive? When either both A and B are above their averages or both A and B are below their averages, A and B moving in the same direction. When is it going to be negative? When they are moving in opposite directions. A being above average means B is below average. So therefore, when I look at this product and I sum it up over all my observations, I will get a positive number if most of my observations are either both above average or both below average. If both are on opposite sides, one is above average and the other is below average, I will get negative. Which would mean that if my data looks like this, R will be positive. And if my data looks the opposite of that, in other words, on the opposite quadrants, the contrarian quadrants, I will get negative. This is called the correlation coefficient, this average. A little cleverness is done, and it is divided by standard deviation, sigma and sigma b. What this does, it does 2 things. Number 1, it removes the units of measurement. The unit of measurement of A into B is the product of the unit of A into the unit of B. So the value of R depends on the units of measurement. To remove this dependency on units, you divide by the standard deviation. And so therefore R is dimensionless. This is the correlation coefficient. Positive for positively associated data, negative for negatively associated data, in the sense of positive variables increasing and decreasing together, negative variables increasing and decreasing as a counterpoint to each other. As one goes up, the other goes down. Here is a picture of what these correlations look like. +1 correlation means that they line up perfectly as a straight line. As we do things like linear regression, you'll see that correlation is actually something that looks at linear relationships more than anything else. -1, the line goes in the opposite direction. 0, there's no line at all. 0.7, there is a line, but not always. Are the two variables moving in the same direction? But most of the time they are. 70% of the time they're moving in the same direction. Correlation of minus 0.4, there is a weakish negative relationship. So the sign tells you whether it's positive or negative. The value tells you how strong the relationship is. +1, a strict positive linear relationship. -1, a strict negative linear relationship. So to end, I want to summarize what we saw. We saw graphical displays of data through histograms, scatter plots, etc. We saw measures of central tendency, means, medians, modes. We saw measures of variation, ranges, standard deviations, interquartile ranges, variances, coefficient of variations, etc. We looked at distributions, and through distributions also looked at ideas of skewness. We looked at summarizing various numbers through 5-number summaries or through box plots. We visualized various things, and we looked at correlations as well. We looked at different kinds of coordinates to be used for multiple plots. And in future sessions, what we will do is we will relate these summary statistics, these descriptive statistics, to inferences that we can draw from data, for which we will need a layer of probability, and also possibly to look at deeper visualization techniques, if and when the opportunity arises to do data visualization as an add-on to descriptive statistics.